Hello, my name is Chirag. In this presentation, I will cover the details of my final year project. This is my poster that was displayed on Spark Night. Legacy networking architecture is the most commonly used networking architecture today. This kind of architecture is built with a cluster of routers and switches that are autonomous in nature. By autonomous, I mean each of the router in the network will need to be capable of performing complex tasks such as calculating the shortest path between two nodes, building network topology, maintaining routing tables, and so on. Another problem is that generally a network is built with devices from different vendors. Each vendor differentiates themselves by having their own proprietary software. For example, iOS from Cisco and Junos from Juniper. This implies that the network engineer who's responsible for configuring these devices will need to be well versed with these operating systems. The biggest change in how these devices are remotely configured in recent years has been the shift from the less secure Telnet protocol to a more secure SSH protocol. However, this does not change the fact that each of these devices will still need to be configured one by one manually. Now, this might not seem like an issue when we think of a simple network like this. However, when we look at a more complex example, it becomes obvious that the task of configuring each and every device in the network is tedious and time consuming. Another big problem is quality of service. For instance, we can think of a scenario where suddenly video packets will need to be set as the highest priority in the network. Since each device needs to be manually configured, the existing tools do not allow this change to happen in real time. In the same context, this project will investigate a new networking architecture known as software-defined networking. In particular, how SDN solves these issues and how the role of a network engineer will change when SDN is widely adopted. The network to be tested has been emulated by using a tool known as Mininet. This is because Mininet is open source and the results from the emulated network is realistic. Although there are other network controllers available in the market, I chose ONOS as the network controller. This is because ONOS is open source and can monitor and configure both IP and optical layers in the network. To further demonstrate network programmability, an attempt has been made to integrate a network planning tool called Mantis with ONOS. Throughout this project, a lot of significant contributions were made. I've successfully implemented an Ubuntu server that can run ONOS and Mininet emulated networks in the same virtual machine. I've designed a Python script to define the network devices that will be used to build both IP and optical layers using Mininet. I've also implemented a TCP server using the iPerf tool to generate TCP traffic to test the bandwidth of links in the network. I've designed an ONOS application that can be used to collect network information in JSON format. I've also implemented RESTful APIs to automatically forward this information to Mantis PCE. I've also designed ONOS CLI commands to interact with the Mantis application, and I've also designed a set of static parameters in JSON format to describe the network in more detail to Mantis. To understand the new SDN architecture, the diagram on the right can be used. The infrastructure layer refers to switches and optical ROADM devices. These devices will need to support protocols such as OpenFlow, NetConf, and RESTConf. The control layer typically consists of the network controller. This controller will configure the infrastructure layer using the appropriate protocol. In this project, Mantis also sits in the control layer. The application layer consists of a graphical user interface that the network engineer can use to operate the network controller. The presence of a network controller has vastly simplified the process of configuring every device in the network. This is because the control plane, also known as the brain of the device, has been removed from the device in the infrastructure layer. Instead, all the algorithms are now installed in a network controller. This means that the network controller will now take care of complex tasks such as finding the shortest path, building the network topology, and so on. This network controller will program all the devices in the network. This is a huge improvement over legacy networking architecture because the network engineer can just configure the network controller, and the network controller will then automatically configure all the devices in the network using protocols such as OpenFlow, NetConf, and RESTConf. Path computation can be a very CPU-intensive task. Since the network controller is responsible for a lot of other tasks, an attempt has been made to offload some of the processing to an external path computation element such as Mantis. The main objective behind doing this was to prove that SDN networks are open and programmable. This is a major advantage of SDN because it puts the power back to the hands of the network engineer. In the older architecture, this was not possible. How each device, such as router and switch, operates was purely dependent on the proprietary software that is installed on that device. Mantis is a network planning and optimization tool. In this project, Mantis is primarily used as the path computation element. The ONOS application that I have designed will collect all the information about the network topology in JSON format. To demonstrate the SDN architecture, the following network has been emulated. Our company has 3 branches in different locations. Inside each branch, the network is built using OpenFlow enabled switches, and the branches are separated by an optical layer. As a network engineer, my job would be to ensure that there is connectivity between each branch. Now onto the demo. Since the network controller is currently not running, there is no connectivity. Once the ONOS network controller has been started, we can now see that we have access to the graphical user interface. The network to be tested can now be emulated using Mininet and Python. As described before, there are 3 branches of this company: branch F, branch M, and branch Z. Each of the branches is built using IP OpenFlow enabled switches, and the optical layer is built with ROADMs that are also using OpenFlow protocol. The network controller does not automatically detect all the hosts. This can be fixed by running a simple ping all command using Mininet. We can now see that the network controller is discovering each and every host that is connected in the network. Clicking on each device will give us more information about the device. And if we go to device view, we can see the number of ports that each device has. If we go to the links, we can see all the links that are in the existing network. If we go back to the Mininet terminal, we can see that all the pings that was initially set up has failed. This is because we haven't told the controller to forward any traffic just yet. To fix this, we can just go to the applications and enable the reactive forwarding feature of the network controller. If we run a ping all command again, we can see that there is connectivity inside the branch. To simulate real traffic, I will set up a TCP server using the iperf command. Host 2 will now connect to host 1 and download some information. We can now see that there is real traffic flowing through the IP network of this branch. If we go to the graphical user interface, we can see this traffic move in real time. We can also see the path that is being taken by the traffic. It is also evident that the network controller has configured all the devices for me. I will now connect to host 1 of branch Z and branch M to prove that there is no traffic flowing between these 3 branches. This can be confirmed in the graphical user interface. The reason for this is that we haven't programmed the controller to forward traffic using optical layer. And this is where Mantis comes in. Initially, we can see that there is no application called Mantis installed in the ONOS network controller. I will now compile and upload my application to the ONOS controller. Now that the application is installed, in the graphical user interface, we can see the Mantis Advanced PCE application. If we go to the ONOS log, we can see all the information that my application has collected from ONOS. A free online tool called JSON Editor Online can be used to make this JSON payload more readable. We can see that the device ID that my application has collected matches the device ID in the network topology. In the ONOS log, we can also see the response from Mantis. We can now see the CLI commands that I created to interact with my ONOS application. Using the Mantis establish connection command, we can forward the static parameters to Mantis. The emulated network that I created at the start of this demonstration does not reveal the true reason why we need to use an external PCE. This is why a more complex example has been emulated. We can now clearly see that calculating each and every path in this network can become very CPU intensive. If I reinstall the application, it will reprint the information it has collected from ONOS into the ONOS log. We can see that this information was indeed not hard-coded into the application. Although my application is capable of collecting the network information from ONOS, it is not capable of programming ONOS with the light paths that it receives from Mantis. This is why the remainder of this demonstration will be performed using the default PCE in ONOS. If we come back to the original scenario, we were stuck with a problem. The problem being there was no connectivity between each branch. In order to solve this problem, we must first check if there's a light path between ROADMs 1, 5 and 6. From the ONOS CLI, we can see that there is actually a path between these ROADMs. But just like before, we haven't told the network controller to forward traffic using these paths. This is done by the use of intents. Initially, we can see that there are no intents installed. To add intent, we must specify the device ID and the port that will be used to forward traffic. From the topology, for ROADM 1, we can either use port 11 or port 10. And it's the same for ROADM 5. When we add this intent, we have told the network controller to forward traffic in one direction only. Because of this, there is still no connectivity between branch M and branch F. To fix this, we just add the intent in the reverse direction. Now we can create a host-to-host intent to tell the network controller to forward traffic between these two hosts. If we go back to the VM, we can now see that branch F and branch M has connectivity and TCP traffic is now able to flow between them. In the similar manner, we can add connectivity between branch F and branch Z. Now we can see that branch F has connectivity to the other two branches. We can also see that there is TCP traffic flowing between these branches using the optical layer. But what happens if a port goes down? In this case, port 20 of ROADM 3 has been brought down. Although the port is down, we can see that the network controller was smart enough to recalculate the path. Because of this, traffic can still flow between these three branches. In this presentation, it was proved that SDN architecture is the future. This architecture allows network to be open. Therefore, it is possible to program the network to work in any desired manner. Big companies such as Telstra, Google, Facebook, and so on are already adopting this standard to improve the operation of their network. SDN has finally opened the opportunity to innovate in an industry that seems to have stagnated in the past 2 decades. Thank you for watching this video presentation.